In this video, we're taking a look at center of mass using integration methods. We are going to have to use calculus to add up various pieces of continuous distributions of mass. So we can find the center of mass of a rigid extended body. Rigid is important because, as we saw with that slinky example, when things are flexible, they get a lot more complicated. So there are lots of different spatial integrals you have to do in AP Physics C. Center of mass is what we're doing today. The other stuff is coming later in rotation and electricity and magnetism. So the big steps here are you slice up your object so that every piece has the same center of mass coordinate. And we either do this in terms of position or area, or a single dimension position, area, or volume. And then we add up to get total area or volume, and then we multiply that by some mass factor. So this is the key idea, though. Every part of the piece has to have the same center of mass coordinate. And so the thinking part, the part you have to actually work on to make sure that it makes sense, is to do this expression for dx, dA, dv, the spatial variables, because you can't integrate with respect to mass. So this is all on page 30 of the packet if you want to follow along with what I'm doing. So if you imagine a circle, now it's pretty obvious that a circle, right, a solid circle or disk, is filled up with an even distribution of matter. We can figure out how to find the area of this circle by adding up little rings, right? So if the circumference of a circle with respect to r, as a function of r, is 2 pi times r, you can integrate from 0 out to some capital R value of that circumference with respect to r dr. So 2 pi r dr, integrate from 0 to r, you end up with pi r squared. So this is really one to show you an example that what you already know about area and volume already works. We could do this with a sphere. Well, the surface area of a sphere is 4 pi r squared, right? And the surface area as a function of radius is 4 pi little r squared. And if we want to know all of it, we can add up all the thin spherical shells until we get to a total ball. Think of it as repeatedly dipping something in wax and giving it another layer and then doing it again and again and again, or maybe peeling off the layers of an onion, although they're not spherically symmetric. But so you integrate 4 pi r squared with respect to r from 0 to capital R. And so you get all these, add up a bunch of very, very arbitrarily thin spheres, spherical surfaces, to get 4/3 pi r cubed, which is, of course, the volume of the sphere. You can do this with other shapes, right? Here's a cone, right? A cone is a little bit more complicated here because each circle, as you go from, say, 0 to some height h, is actually slightly bigger. But each of those circles has an area that is equal to pi r squared. And that r, the radius, depends on the ratio of capital R, the maximum radius of the circles in the cone, over h times how high up you go, right? When you get to h, you should get r. When you're at y equals 0, you should have 0 for the radius. And so we're going to integrate this area with respect to y, which is pi capital R squared over capital H squared times y squared. We integrate from the bottom, 0, all the way up to the top, h, with respect to y, and we end up with pi r squared h over 3, which, if you look up your area, volume of a cone, is what you would get. Continuing on then, we have the problem of finding the center of mass of this object. Now, if we can find the volume of the object, we've done the hard work for figuring out the actual integration. Now we need to figure out how to use that with what we know about an object and finding its center of mass. So if you look at this cone, it's probably pretty obvious that if the density is constant, or if it only depends on a known function of position, we can figure out the center of mass by adding up all these little pieces. So lines, plates, cones, etc. work on this. We already know that for a system of particles, right, you can add up discretely the individual particles. Well, it also makes sense, I would hope then, that if the object is continuous, you could add up tiny little bits of mass, dm, if you will. And so we're going to take little slices and say there's a little bit of mass there, and each dm has a position, right, along the y-axis, and it's all the same on the x-axis in this case. So the x center of mass is going to be 1 over the total mass divided by the sum of all these little pieces. But if those pieces become really arbitrarily small, dm's, instead of discrete masses at individual positions, they're x dm, and still the 1 over mass is there. There's a problem. I can't differentiate 1 kilogram of mass from another, right? They're all the same. And so what would be easier to do is to integrate through space to find this. So how do we do this? Well, we use what we know about density, right? Things with uniform density, everywhere in them have the same ratio of mass to volume. And so what does that look like? Well, there's volume density, rho, that's a rho, is total mass over total volume. And if the density is constant, then every little bit of mass divided by every little bit of volume should be the same. If it's surface, then it would be sigma, that's a sigma, mass divided by area, and every little bit of mass divided by every little bit of area. Or it could be even a linear density, which we call lambda, mass over length, dm over dl. And so we can rearrange that to say dm is rho times dv, dm is sigma times dA, or dm is equal to lambda dx. So we can now use linear surface or volume density to get an expression for dm with respect to a variable we can actually use to integrate, a spatial variable, right? So we're going to replace that dm to use this to solve. So a couple of examples here. I've also written these out and posted them in the homework solutions, but there are 5 steps to this. First, we pick axes and coordinate systems, always. Make a prediction about kind of where we think the center of mass is to check our result. Write out the center of mass equation in terms of dx, dA, or dv, and then we decide how we're doing the slices and make sure they're all working so that they all are along the same axis or something like that. Then we actually write out the integral in terms of a single variable, x, y, or z, not, or r in some cases, not area or volume, and then we integrate. So if you take a triangle, right, this is a surface density, sigma, we want to think about what we have here. Well, the first thing to consider is that if it's a surface, sigma is dm over a, so dm equals sigma times dA. And if I want to know the way mass is related, well, area is really just width times dx, right? That's what this next line is. Here, I'll use my laser pointer. But of course, the width can be found as a function of where you are with x. When x is 0, the width should be 0, and when x is h over here, then the width should be w. And so if we use all these substitutions into our basic formula and use the fact that the mass is equal to the volume times sigma, we can also say that the volume, or the area in this case, is height times width 1/2 times sigma. We plug that into our original equation, replacing 1 over m with 2 over h w sigma. We're integrating from 0 to h of what we substituted in for dm, and we still have that x term in there, so we now end up with an x squared. We integrate from 0 to h, we solve, and we find out that our center of mass is at 2/3 the height of this object, or of h. We can do the same thing with a cone, which is no different than the triangle, except that it adds an extra dimension. We still do the same basic thing. Now it's mass over volume. We're replacing dm with rho dv. The volume little bit is the area of a disk times the height dy. The area is just pi, r squared, where the r at that point has to do with capital R over h. So we get that same relationship we got before. And we can integrate and find out that the center of mass is at 3/4 h. All right, so continuing on then, if you want to look at something like a rod, which seems pretty simple, but what if the rod does not have a uniform density? What if instead of just being lambda, some mass over length, it actually gets denser as you move along it? There's lots of application for this, like a column of air actually has a variable density and so on. But for now, we can just use a simple one-dimensional object with a linear density. This is probably more applicable to something like linear charge density, which we'll get to again later, than mass density, but it still works. In this case, the big change, everything else in the setup is the same. The x center of mass is the integral of 1 over m, or is 1 over m times the integral of x dm. We're replacing dm with lambda dx. But lambda is no longer something that is a constant. It is now in terms of x. And the total mass of this is something else we need to figure out, because the total mass will actually be adding up all the little bits and pieces. So this is actually going to have to be an integral from 0 to L of lambda dx to actually find it, which is x over L. And that's how we got the total mass. But once you find the total mass, you can plug that in. We have a few extra terms here, and we find out that the center of mass is 2/3 L. All right. There are a few more examples in this slideshow that you can go ahead and look at if you are interested. And then there are, of course, the examples in the homework solutions that you can look at. But that is the basics behind integration to find center of mass. It will take you some practice, and I am sure that you'll have questions, and we'll work on those together in class tomorrow.